So we've covered quite a bit of ground on convolutional neural networks. So we know the different types of layers and nodes and functions that we can use, right? So there are the convolutional layers, there are the fully connected layers. We have also talked about different activation functions that we can use, linear and nonlinear functions, the pooling layers to reduce the amount of information that the network has at a specific time so that you actually simplify the computations. Batch normalization, super important to add batch normalization, otherwise the gradient as they go down backwards, not the forward algorithm, but the backward algorithm, as you keep reprojecting the gradient back, the gradient keeps decreasing in value, right, in magnitude, and basically after just a few layers it disappears, so the network can't learn. Batch normalization is just a simple trick to keep the variance of that gradient large enough that it allows the network to keep learning. So we've talked about ways also to initialize the network and other tricks that you can use. If you really get desperate, and I mentioned this because, I mean, it's not unusual to get desperate with these big networks, and when we see today, probably if we have time, but if not, certainly in our next class, when we see the different types of networks that are used these days, they're so enormous, right? They're so large. Training them can become a nightmare, right? So one of the things that one can do is to do better pre-training. So to pre-train the network. And I've already talked about pre-training, remember? We've spent some time defining algorithms, but there is another one. It's another way to pre-train your network that I wouldn't necessarily encourage you to do it right away, but if you get desperate, if your network is not learning, then you should try this. And the idea is to first train your network in an almost unsupervised way, okay? So imagine, I always give examples in computer vision, but the same applies to any type of input features that you may have, right? So imagine that you have a set of images, right? And they represent, I don't know, maybe they represent cars, cats, tables, and so on, right? Faces. You can also have digits, right? You can have the digit 0 up to the digit 9, and that's what you want to learn, right? So imagine that you're doing digit recognition. This is a difficult task because when you have handwritten digits, everyone uses a different style, different font, what have you, right, to write. But how about if I now give you a set of images with random noise, okay? These images just have random noise right here. And the task now is to learn to differentiate between these two, right? To know whether you have a digit or you just have random noise, right? So that's a possibility. Now possibility is just to learn to represent all that information, right? Find a representation. And we have already seen how to do that, right? How do you learn to represent that data? With any model that we have introduced before, right? For example, one could use a Gaussian model, a mixture of Gaussians. Even more simplistic, one could use PCA, ICA, factor analysis. Let's talk about these later ones. What these are in neural networks are equivalent to what's called an autoencoder. And what this is the following. I have my input nodes, right? I'm going to write the inputs down here. So let's say the nodes of my graph for the input correspond to these nodes right here. And those may correspond, for example, in computer vision, correspond to the pixels of the image, for example, right? Or windows, average windows, or what have you, of the image. In sound, they could correspond to specific periods of time of the DCT representation or the sound wave, etc. Okay, and now what I'm going to do here, I'm going to add a hidden layer, right? Remember, hidden layer is any layer between the input and the output, right? A hidden layer and the output layer, okay? And here I'm going to have the output layer. Now, my input is going to be X, or maybe at a certain stage, let's call it W at a certain stage of the network. So at the beginning, that W would be X, the input. And then what's this going to be? This is going to be, remember, my latent representation, okay? So this is going to be my latent representation. Space defined by a variable z vector, right? The z vector that's given by these nodes. And here, what I'm going to try to do is to reconstruct. I'm going to try to reconstruct my input from that latent representation, that hidden representation, right? So I'm going to have these nodes connected in some way to this layer, and then this layer again to these other nodes, right? And now I train this, right? So here's what I do. I take the input layer and the first or the next layer, right? And then I add this. This is not in my network, but I add this, and I train these first two layers, okay? Now, once I'm done with this, I take this one and I move it down here, right? That's already given to me. And I put in the next latent, right, which is the next layer. It's the next latent space. And I add this as new, and I try to reconstruct the information of the previous layer. And I keep iterating this. You see how this works? So if I have a network with multiple layers, like this, now a box is given by one of these things here, right? Right? So first I take this first layer, right? And I put it here. Well, first time maybe I'll put it here because this is going to be the input in that particular case, right? And I try to learn this with, say, just random information and actual data. So I'm just trying to make the network learn to represent images, period, right? This is the same, again, as PCA, what PCA did, ICA did, what factor analysis did, right? It's exactly the same idea. Now, once I have achieved that, and I have learned the weights for these edges here, now what I do is I take this as my input, this is fixed, and I move this into the hidden layer, and I add this as an extra, and I learn again, right? So now I'm learning these other weights, right? And I keep moving forward like this until I learned all the layers, all the information, all the layers. This is really expensive to do, so I didn't do it unless you have to. But it actually gives you an initial value for the weights that knows how to represent the data that you're dealing with, right? And that gets you at a better starting point to apply gradient descent. So you're actually able to find the solution that you're looking for in some, say, polynomial time, right? Which is our goal usually. Okay. All right, any questions about this? All right, now make sure that you know all these things, that you practice. There's only one way to learn to work in deep learning with deep networks is to practice, right? So when you submit your homework, your projects, we will know whether you have done the right thing or not by just reading your description in your document, right, in your report. That tells us how you initialize your weights, how you trained the network, what things you did to make it successful, and so on and so forth, right? That's very telling. Anyone that has worked with deep networks will know whether you know how to train a deep network by just asking you questions about how you initialize the weights, how you apply gradient descent, how you normalized your gradients, and so on and so forth, right? These are essential parameters to know. All right, so moving on, then, I want to talk about two things today and in our next lecture. So I'm going to spend quite a bit of time discussing the two things that we now need to do. So we have all the elements that are required to design deep networks, okay? You know, how to, which different types of layers you have, which different types of activation functions, and so on and so forth, right? And the way you design a deep network is by doing this, right? By just putting blocks. So you first design a block by saying, okay, this block is going to be this convolution. Right? It's going to be a 8x8 convolution with that kernel to do the convolution, right? That's it. That's your block. You put it here, maybe here, maybe here, and so you specify where you put the convolution, right? Then you say, okay, I'm going to put pooling layers once in a while to reduce the complexity of the representation, right? So I'm going to put it here, and so on. And I'm going to use batch normalization to help me solve the gradient, the problem of diminishing gradients. And I'm going to put it here, 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 and here, and so on, right? And that's how you build them. That's it. Simple as that, right? Okay. One thing that we need to know is what works and what doesn't, right? So I'll spend a lot of time actually discussing what people have done and what architectures, which of these architectures seem to be performing better than others, okay? And the other one that I want to talk about is the loss function, right? The loss function is what am I going to add at the very end, right, of my network when I compute the actual output that that network is giving me compared to the desirable output, right? Remember that as always, I have my training data. My training data is nothing else than a set of, let's see if I can find something that works a little better. My training data is nothing else than a set of xi's, right, my input vectors and corresponding yi's from 1 to n, right? This is my training set, right? And now the network is not going to output y, right? So if I do f my network, right, my function that I've learned with the network, if I do f of xi, I'm going to get, let's say, yi hat. That's the output of the network. And now what I want to do, I want to compare yi hat with yi, right? And now remember, given that loss function, I compute the gradient of that loss, right? And I backpropagate that gradient through the network, right? That's how we do it. If I use a stochastic gradient descent, remember, I do that one simple at a time. A stochastic means I randomly select an xi, and then I just apply the gradient to that simple, period, right? Given by this loss. If I use batch gradient descent, then that means I use the whole set. And if I use mini batch, means I use a subset of this, okay? But they're all based on the same idea. They all need to use that loss. And that loss is as critical, if not more critical, than the architecture, okay? So I want to spend now some time discussing how on earth are we going to define that loss, determine what loss we want to use, and what associated optimization methods do I need to be aware of for specific loss functions. Now, not all loss functions are created equal, and not all optimization methods are going to work for every loss function. Again, my goal here is not to do optimization, to convert this into an optimization course. We have 2 beautiful courses that we teach in the department that you could take, and I encourage you to take, that will teach you how to do all these optimization, or how to build these optimization algorithms, or use these optimization algorithms, okay? But we need to know that these optimization algorithms exist. Otherwise, we don't know which loss corresponds to which optimization and so on and so forth. Okay? So you could interpret this next topic as how to select a loss function for deep networks, right? Why don't I say that? How to select a loss function. Again, if you want to work in deep networks, you need to understand two things, the loss function and the architecture. These are the main two components, right? And then you need to know how to actually learn, right? How to make this learning process work. All right, so first, we need to know what makes a good loss, right? What does it mean that a loss is a good loss? First off, a loss needs to be differentiable, because if I cannot differentiate the loss, I cannot calculate the gradient, I cannot backpropagate the gradient, right? So that's a given. Either the loss is differentiable, and it's okay if it's not differentiable. Make a note to that. This is extremely important. Write it down. It's okay if it's not differentiable in a finite number of places. That's fine, because you can deal with this, right? If you have the L1 loss, right? L1 loss, remember? The one norm loss looks like this, right? Not differentiable right here. Who cares, right? We can avoid that point. This is solvable. That's not a big deal. But it has to be in a finite number of places, okay? Everywhere else, it has to be differentiable. Okay. For example, we have talked about the 0-1 loss. Remember the 0-1 loss? Terrible choice, right, for deep networks. You can work with a surrogate of the 0-1 loss that is continuous, but you cannot work with the 0-1 loss because it's not differentiable, right? So it's not a nice function to use. The hinge loss is differentiable almost everywhere, right? Remember the hinge loss? It looks something like this, right? So it's linear here, and then it's 0. After that value that we show, it's equivalent to the logistic regression value, right, of 1. Okay. So hinge loss, it's a good choice, and it's been a very one of the preferred choices for many people for years. Not so much in recent times, but it was very popular just a couple of years ago, a year ago. What also makes, so this is not so good, the hinge loss good, the square loss good, square loss or the least squares if you prefer loss, right? Meaning the square. All these are good choices, okay, differentiable. Another much preferred loss function that you'll see in the literature in deep networks, it was probably the most popular loss function for a while, is softmax. Now, softmax is nothing else than logistic regression normalized, okay? And it's the adaptation of logistic regression for multinomial logistic regression. That was defined, I don't even know, softmax, maybe in the 40s. It has a long history, but it has found, you will see with what we're going to do in the next couple lectures, that many of these results that were first derived in maybe the early 20th century, some of them even the 19th century in statistics and mathematics, are now resurfacing as really good things to work on. Right? So softmax was a really good option just because it's a logistic regression solution, right? So that was also very good. Now, This is what makes a good loss, right? Differentiable, except at a finite number of places, okay? Ideally, twice differentiable if you can't. So you can apply second order gradient methods. Remember, like Newton's. Newton's needs the Hessian. You need to compute the Hessian. And that requires a second derivative, okay? If not, you just need to use first order methods. There's nothing wrong with that. But now, so far so good. But remember, I've already mentioned this. A loss function, typically, you need to add a regularizer, okay? I mean, this is a must. I can't imagine you succeeding in making the system learn without a regularizer. I mean, some people do it, but it's tough, right? Tough enough with a regularizer, let alone without it. Now, remember the reason why we add a regularizer, right? There was a comment from one of you when we introduced this, that it solved the problem of singularity, right? True, yeah. That's true, but that's not the main reason why we want to add this. The main reason we want to add this is because it adds stability into our solution. And think about this. If I have my space here and I have an unconstrained loss, right? I have a complex loss that has, say, a loss that's defined given by a higher order polynomial, then I may be learning something of that form, right? But by adding to this simply the square loss, right? Norm to square loss, then I am going to smooth this out to something like this, right? And that will add stability in my learning, because the network is not trying to carve its way into every corner of the feature space, trying to learn every single detail or nuance of the data, right? So in a way, you're assuming that these nuances or these carvings here correspond to noise or things that will not generalize. Remember, generalization means that I learn from a specific data set, training set A here, and then when I test for an independent test B, the system still gives me good results or equivalent results to the ones in training. That's generalization, right? Another thing that I can do in learning is memorization, right? I can memorize A, and yeah, after I memorize it, if you give me an example of A, I can give you the solution. But if you give me an independent sample that does not belong to A, then I have no idea, right? So I'm going to do poorly. See the difference? So there are many ways by which I can learn. Memorizing, bad idea. Generalizing, great idea. So that's expected to generalize better. Again, back to the central limit theorem. That is not a guaranteed, but in practice, that's what people have found to work better. And remember, this goes back to overfitting, meaning that I try not to overfit to the training data, okay? Or at least not too much. Now, there's also a theoretical result in optimization that shows that when I add specifically the square loss, when I use specifically the square loss, it's been shown that in general, that makes a loss function with a regularizer added, that is the square loss, it makes a stochastic gradient descent equivalent to the actual nonlinear least squares gradient descent that we originally introduced, right? Which is a really good property to have, because we know that's a really well-defined algorithm. One way to let the algorithm adapt to a specific regularizer that helps you is by using a method that I've already introduced, I've already mentioned before, which is called adaptive gradient or adaptive backpropagation, comes by different names. And for short, people just say at the grad. Okay. I always say Ada grad because it reminds me of Ada Lovelace, but it means adaptive. So, anyways, a way to remember. So, and these algorithms should be implemented in all the platforms that you use, and that's a way to use a regularizer that adapts to it. All right, more things about the loss function. Generally, you want what it's called well-conditioned functions, okay? And I'll put this in quotation marks because all these things that we are describing are, they have to be taken with a grain of salt. Okay, so what does it mean that a function is well-conditioned? In general, what it's going to mean is that if I have a function, my function like this, that is convex, that convex function is bounded by two other convex functions above and below that look like this, okay? If my function is bounded above and below by two other convex functions, then I'll say generally that this is a well-conditioned function. Why do I care about well-conditioned functions? Because in general, if my loss function is well-conditioned, then I can learn using gradient descent in polynomial time. Okay. So for example, piecewise linear functions like the hinge loss, remember? These are not well-conditioned functions, right? Because it's piecewise linear and it just cannot bound it. The square loss, however, is still well-conditioned, and the logistic regression function is also well-conditioned, right? Softmax as well. Of course, what am I going to do if I want to use the hinge loss? Any ideas? So I just said the hinge loss is not well-conditioned, right? But let's say that I do want to use the hinge loss. How can you solve that problem? I add a regularizer, the square loss. That's it. That's simple. That's how important regularizing is in these loss functions. So we can still do it. We just need to add the right regularizer in the right place. Okay, as a side note, I'm just going to make a parenthesis here. There's a recent optimization solution that combines both batch and stochastic optimization in a single algorithm. And this algorithm is called variance reduction, and it's worth mentioning. And the way this works is as follows. You take the value at t plus 1, remember t the time, okay? So at t plus 1, you take x of t minus nu, or is that nu or eta? Anyone remembers? Okay. Eta, probably. Eta which is anyone remembers what this is called? Loudly. Yeah, the learning rate, right? Remember? Okay. So I'm going to take the gradient of f at xt. So I'm going to add this tilde on top of the gradient to specify this is not the gradient of the function f. This is the gradient at point xt for the function f, right? That's the stochastic gradient. Remember? For stochastic gradient, I only take the gradient at that one point. I don't compute the gradient of the whole function, just at that point. So I'm going to write this gradient, stochastic gradient of f of x, and now I'm going to subtract the stochastic gradient of f of x0 being at time 0 or at some reference time that I have set as 0, okay? And now I'm going to do plus the actual gradient of f at x0. Now, note this is the stochastic gradient at x0. This is the actual gradient of the whole function at time 0. Okay? So that's a full gradient. So what does this mean? This means that this algorithm, this idea of the variance reduction algorithm, variance reduction minimization, if you prefer, is that after every, say, I don't know, 10, 20, p in general, right? After p iterations, I compute the whole gradient for the function that I have at that time, right? I compute the actual gradient, f, right? This one, gradient of f. And then for the next p iterations, or p minus 1, I just use a stochastic gradient descent. But I subtract the stochastic of that point where I did the computation of the whole gradient and substitute it for the actual value of the whole gradient. Okay? I think it's a pretty neat idea. And some people say that this works better for learning some of these networks, right? Because obviously, as I said many times, ideally, yeah, you want to use the whole gradient. If you can't, it's just computationally expensive, right? Especially as the training set grows larger and larger and larger. So it's a chicken and egg problem. Deep networks can only exist if you have a tremendous amount of training data. Because if you don't have millions of data points, how are you going to learn millions of parameters that these networks have? It's impossible. But if you have millions of parameters, then calculating the gradient, for example, doing batch gradient descent, it becomes computationally too expensive. It's impossible. It becomes absolutely absurd. So you have to simplify the problem, right? And that's one way to do that simplification. All right. Now, unfortunately, note that this is for first order gradient descent. This was proposed a few years ago, and I am yet to see an extension of this to second order methods that can calculate the Hessian as well. So maybe someone has proposed it, and I'm not aware of. It's possible because there are like 100 papers published every hour on deep networks these days. Or in these optimization methods. So you may want to check, but if not, hopefully someone will propose a method soon enough. But be aware of that and look for it in the softwares or in the libraries that you may want to use. That's a very good idea. All right. The next thing is to use conditional gradient descent. Now, until now, everything that we have done today is for unconditioned, right? But generally, the space of possible functions that I'm looking for, remember, a deep network is nothing else than a regressor, right? And it's trying to find a function in my space H, remember that space H of all possible functions where I'm allowed to search, right? Say all the polynomials of degree 2 or all the polynomials of degree smaller than 5, what have you, right? Well, that space may be too large for me, right? The problem is that ideally I want to search the whole space, but using gradient descent is insane. I'm never going to find the right solution if I search throughout the whole space. So I want to restrict the space H to a subspace, okay? And that's where conditioned comes into play. So here I want to minimize, as always, my function f of x for my x in K, right? So K here, a convex region. Convex region. Right? So for example, you might have something like this. If my H space were three-dimensional only, I can't imagine how, but if it were three-dimensional only, maybe I want to restrict my space of possible solutions to this region right here, okay? You see how this works? So this would be my K, right? Where I want to restrict my solution vector has to be within that convex region, right? For example. Okay. Now, computing the gradient is not too expensive, right? So one way to work with this, what one could do is to let's say that I start with a point right here inside. This is inside my region K, right? And now I compute the gradient, which goes in that direction, right? And I move about the gradient. I end up here, which is outside the region. And then what do? I project orthographically onto that region, and I find the closest space that it's in that region, right? But this orthographic projection, this reprojected projection into this space, right, onto that subset, that's costly. That is very computationally expensive, right? So you want to reduce this complexity. And the way to do this is by using a method in optimization defined in the 1950s. I told you that all these things are coming back, right? Which does the following, that defines v of t as the argument that minimizes the x in my convex space K. So here I compute the gradient of fxt times x, and then I compute the reprojection, or I'm sorry, the next step of the learning as eta t of vt minus xt, okay? And this is basically one of the methods of momentum that, or similar to momentum, that we had defined earlier. There's also an online version of this algorithm that seems actually pretty useful. Okay, so far so good. One more thing. Remember in like our first lecture maybe, when we started defining the different types of features that I might have, that we said, well, usually I have continuous features, right? I'm usually in the real domain of p dimensions, right? RP. But I can also have discrete features, right? I can also want to do discrete representations of things, right? So in that case, you need to be careful. So you need to define discrete loss functions. So let's see how we can do discrete, discrete loss function optimization, okay? So let's start with a discrete set of possible features, or either features or set of functions, okay? So my set of functions I'm going to call it that V. Is that new? Then? I don't know. How is this called? What's that? New? OK. All right. So I found my new. OK. So this is new 1 through new, what did I say? C, for example. OK. And now we want to work with a loss function, right? So I want now to define a loss function that has the form f 2 to the power of nu, right? So I'm taking values in a discrete space, right? Either in or out, right? 0 or 1, or -1 or 1, right? And from this to a real number, right, that measures the similarity. This is what the loss function does. And let's see how we can do this. So for example, just to give you an example, you may want to have f of 2 possible values, nu I and nu j, to be equal to yk, right? To some specific output. And the goal here, the optimization goal, is to minimize my function f of s, I'm going to say, of my set s, for every possible s. Okay. Okay. So now remember I talked about what defines a good loss in the continuous domain. What defines a good loss here? In general, a good loss is given by those that satisfy 2 properties. Okay, number 1, let A be a subset of B, and A, B, and an element of the set E be subsets of my set nu that I have defined, okay? That has all the elements. So far, so good? Then f of A union my element E, that means that I take A, which is smaller or equal than B, and I add E. I add an extra element to A, okay? Minus f of A, right? So what does this measure? This measures how good this is compared to how good this is when I add 1 additional element, okay? This is larger or equal than f of B union E minus f of B, okay? Which is the same but for B. But B is larger, right? So what you want, obviously, is that when I add something here, I add E either to B or to A, right? E is neither in B or A, right? So I add it. So I make A larger, but I make B larger as well, right? But because B is larger than A, I expect adding E to A to be better than adding E to B. Okay? This is known as the rule of diminishing returns. It gets to a point that adding more data or more features into your representation or into your data set is just not helping that much. At the beginning, it helps a lot. And then later on, it helps less and less and less and less. And the larger your set becomes, the less it helps. So this is called diminishing returns. And the second one is, again, let A and B be subsets of nu. Then I have that f of A plus f of b have to be larger or equal than f of a union b plus f of a intersection with b. Okay? Now, the functions that abide by these two rules are very famous and very useful in optimization. And they are called submodular. Submodular functions. Okay, so for example, if we were to define a function, this is just an example here, if I were to define a function that simply adds all the weights in my graph, in my DAG, so I have a direct acyclic graph, and I decide to add all the edges, right? So that would be the weights in a weighted graph, right? That would be a submodular function. So you may recall from this, actually, when we talk about independent components analysis, that we were interested in computing the hidden representation, the latent representation, right? So we wanted, say, Z1, Z2, all the way to, I don't know, ZQ, whatever it was, right? So now consider these as nodes, consider them as nodes. And what we had were observations, x1, x2, xq, right? These were our observations, which are the observable nodes, right? So you can represent these two variables here like this. And we showed that you can compute the independent components using the entropy, remember? So I can compute the information of z given x is equal to the entropy, right? And the entropy given, say, xe, if you will. Which defines our observations. Okay, so this is the uncertainty of our latent and the uncertainty given the specific observations. I don't know, you can say E or S if you prefer for the set that we have selected. Maybe S makes more sense. So this function here that we defined, that we used early on for dependent components is also submodular. So all these functions are really good for optimization. And the reason we are very interested in submodular functions is that, or the reason they are important is because they can be optimized as convex continuous functions. So this, I'm going to write it down because this is really important. So this, any submodular function can be optimized as a continuous convex function. Now again, there are methods in optimization that do that for you. You just need to know they exist. And the best way to do this for this type of submodular functions is to use what's called the Lovasz extension. So if you have this discrete representation or a set of elements and you want to define a loss function, and you define a loss function that is submodular, then you can use the Lovasz extension to find a convex surrogate function that can be optimized with classical optimization methods. Really powerful. And typically what you want to do to obtain this Lovasz extension is to regularize by or with, anyone wants to guess? The square loss. Very good. Right. It comes back to this over and over again because there are all these beautiful algorithms in optimization that we can use when we do that. Okay. And by the way, I believe, I'm not 100% sure of that, but I believe that it's shown that when you use the Lovasz extension, probably with the regularizer or not, but most likely with the regularizer, then that the gradient descent algorithms guarantee you solution in polynomial time, right? Which is what we always want, remember. Okay, so another application of all this in deep networks, an important application in deep networks, is as follows. So imagine that we have a latent representation ZLK in my network, which is the result of FLK, the sum over all j of WLJ K Cj K minus 1. Okay, where the weights W L J are all positive or 0, right? K specifies the layer in my network, okay? So that superscript here specifies at which layer of the network I am at. And remember, I use Z to represent a latent variable because in the hidden layers, those correspond to latent representations to which I don't have any control of, right? Other than just using the right loss function to change the weights. Okay, so these are the weights, and these are the inputs to that layer, right? And the inputs to the layer are the values of the previous layer, right? Because this is a DAG, directed acyclic graph, right? So it goes in that direction. And this is my activation function, obviously, right? Now, some people call this deep. It's just funny. You add deep to everything these days. Deep submodular functions. That's just funny. Now, the important thing here is that this function f, the activation function f, can be either convex or not. Okay? Does not need to be convex. And still remember that we assume that the input, right, in this case is either 0 or 1 or negative 1, 1. It's a binary input. All right, there is a, so everything that I said about modular functions applies to deep learning because of this, right? If you have that type of input. So in that case, you want to use the Lovasz extension. There's an interesting survey that was published a few years ago that I'll put in Canvas that in case you are interested in this specific topic. That's actually very useful as a summary of all this. Another reason why this is useful in deep networks is because of big data in deep neural networks. So as I said earlier, deep networks require very large data sets, right? And generally, the larger the better, right? But we have this law here of diminishing returns, right? That it gets to a point where, yeah, you know what, adding additional samples, right? Now, these are not features, but samples. Adding additional samples help, but, you know, not that much, right? So at the beginning, if I have a small data set, I add 1 point, 1 additional sample, and all of a sudden that difference is huge, right? The gains that I make. But after a while, you know, when this is very large, the gains that I make are very small, right? So is it worth spending the time? So we can use the approach that we have derived here to select a subset, let's call it maybe capital X tilde, right, which is a subset of my original capital X, which is the set of the xi's, yi's, right? Such that when I add an additional sample to it, the gains that I make are smaller than a threshold. So what you want to do then is the following, and this is key. You want to find that subset, and that's not trivial matter, right? You want to identify that subset that allows you to obtain reasonable results, right? That when you add more samples, you don't make much progress. You make progress, but not a lot of progress. So you want to first identify this. Once you identify this, you train your network with that subset. And when the network is trained or almost trained, then you finish the last epochs of the training cycle with the whole training set. Okay. Now, how do you select this X tilde? One way to do this is if you have access to GPUs or multiple computers, is you divide the original set into subsets, right? Completely independent subsets. And you, using your network, you see which elements of each subset actually gives you the rule of diminishing returns, right? Or do not break the rule of diminishing returns, right? And at each machine or GPU, you get in parallel the elements of your set that are ideal to train your network with, right? And then you can do a final pass with all these elements of these subsets that you have selected to select the elements that conform to X tilde. Okay? That's one way to do it. There are other ways, but that's one way to do it. All right, so this is a constrained version of the approach, obviously, and you can describe it as the maximization in that case of f of s, subject to, this is my constraint, that the size of that set S has to be smaller or equal than some size Q, right? So we limit the cardinality of this set. Now this problem, unfortunately, cannot be solved with the Lovasz extension. Too bad. But there is another method called multilinear extension, right? So instead of the Lovasz extension, you use a multilinear extension in this problem, which gives you a reasonable solution as well. So to summarize, if you have an unconstrained optimization problem, use the Lovasz extension. If you have a constraint, use the multilinear. Now, don't stop there. Every time that you want to define a specific loss function, a specific training set or subset, and so on and so forth, look for the specific cases, because there are people in optimization that have actually designed very efficient algorithms for very specific loss functions or for very specific data sets, right? Look for those, because obviously if there is a specific algorithm, it is likely that that's even going to be better than any of these general methods. Okay, so deep networks are great, but you need to be very proactive, right? There is a lot of research you need to do every time that you want to design a new network because of all these things, all these different things that are out there. All right, more things. Another way, well, actually, hold on. Okay, yeah, sorry. All right, another thing that you can use, it's what's called semi-gradient algorithms. So let me very briefly talk about those as well. All right, semigredient. It's actually quite popular. This is again for modular functions. F of s, subject to some constraint, okay? All right, so this algorithm can be summarized as follows. First, start with an initial guess for S, and then I'm going to repeat. Approximate F by a modular function let's call it G at that set at that point, and now that point is a set, right? Set the initial guess, and now modify S by finding the argument that optimizes G of my S, subject to my constraints, obviously, and until convergence. So how do we do this? How do we find a modular function? and a modular or if you prefer, you can call this a lower bound, okay, of your function of f always exists for submodular functions. So if this is my function f at some point x, then there's always a lower bound or modular function here, g, that approximates my function at that point, right? So it's just a lower bound. So in computer vision, for example, you will see this used for image segmentation, which is the same as clustering that we have defined here in machine learning. And what it's done is it uses this approach to find graph cats. So you define each pixel of the image as a node of the graph, the edges as defining the similarity between these nodes, and then you find cats, meaning the separation of subsets, right? The subsets that you're looking for, they're more similar within the subset and less similar across subsets, right? That's what you do. And if you use this algorithm, you get an algorithm that's called cooperative cat. There's a find in 2011 that uses this. All right, one final thing, last one, with regard to this, and then we'll see an example, okay? Now, there is another thing that you can use, which is called automatic differentiation. And actually, very few people know this. It's interesting. Or AD. Back in the 50s, 60s, and 70s, when all these methods were defined for gradient descent, this idea of automatic differentiation came out, and interestingly, it deviated. It moved into areas of physics. They used this a lot in physics to simulate models, and other areas of engineering, but it was left out. It was disconnected mostly from machine learning. And now it's coming back because in deep neural networks, we need to generally test a large number of loss functions, right? So as I said, I've give you a quick overview of methods that you can use to define loss functions, right? But I haven't told you yet how to define your loss function. I'll just give you one example, right? But the thing is, your loss function is going to be defined specifically for your problem, right? There are no magic bullets here. So because you're going to have to define your specific loss function, you're going to probably have to test multiple loss functions. And every time you have to define your loss function, you need to compute it, you need to differentiate that, you need to make sure that it's differentiable, and so on and so forth. This is very slow, right? Can we find an automatic way to actually solve this? And that's what automatic differentiation actually does. Automatic differentiation, it's a way to actually let the software do the differentiation for you, even if your loss function is defined as an algorithm rather than a function. Okay, that's pretty cool. That is not the same as symbolic differentiation. So, meaning automatic symbolic differentiation. Automatic symbolic differentiation is the classical differentiation that you'll see in Mathematica, right? So in Mathematica, great software platform. You put in your function, you plug in your function, you ask it to differentiate, and it differentiates it for you. You can even ask to simplify the function, right? And it works pretty well, honestly. That's great, but that's not this, right? That's not what this is. And then there are also, as I've already mentioned here, ways to compute the differentials numerically rather than symbolically, right? That's not what this does either, okay? This is completely different. And unfortunately, I don't have time to cover this topic in detail, but I do want you to be aware of it because it's very useful. So if you have, remember, your learn function, let's say f of theta, the parameters, that goes from some space of n dimension to maybe m dimensions, or I usually use p and q. And your loss function, say it's q of f theta xy, right? And now remember your input in that case would be in n dimensions, and your output would be in m dimensions in this case. Then the optimization algorithm is the argument that minimizes the sum over all I of q f theta xi yi. Okay? So what you're going to do is implement this as an algorithm instead. And use a library that has this. If you're using Python, I believe Julia has this implemented already in its platform. That's my understanding. But if not, you can get a library which is called diff-sharp. That will allow you to compute or to calculate the differentiability of the algorithm itself. And basically, this is just a trick that these libraries do. And what they do is for every variable x that you have, they keep another variable, call it x prime, right? That keeps track of the values of x, so it can actually keep computing the derivative at the same time that it computes x, right? It's a simple trick, but it's a very useful trick. But what this allows you to do is it allows you to try a large number of loss functions very quickly to see whether things work or not, and then decide which one you really want to work out in detail yourself, right? In this library, diff-sharp, you have k-means. I think probably mixture models. Many of the algorithms that we have derived here, maybe ICA, others, implemented already using this approach. They're already here. And they're all like, I have a few examples here, which I don't have time today, unfortunately, to cover, but I mean, it's like, 5, 6, 7, 8 lines of code. That's it. That's all it takes. Very useful. All right. As a last thing, as I promised, I want to spend some time going over one example of how to define one of these loss functions. Okay? Now, I have very few minutes, but I'm going to try to do my best. All right. I'll post a paper that does a nice, it's a good survey, good summary of all this, which is of the same authors that define or implemented that library that I mentioned. So I'm going to show you an example in computer vision of how one goes about defining a loss function. And this is really the main goal for you when you define deep networks, right? Your main goal is to define your problem and then define the loss function that is specifically derived for your problem. So Again, this is just an application in computer vision. Okay. So my goal is to define a mapping. So this is my goal. Define a mapping function f from my image I sub I, given some parameters, right, onto yi. So I, capital I, sub I, it's the ith input image. Theta, the parameters. Typically theta, right? Typically, remember, theta will be the weights in my network, right? And yi is a vector, an output vector, that, for example, in computer vision can be the two-dimensional coordinates, u and v, the image coordinates, of the location of an object that you're looking for in the image, right? I'm looking for a face. So the center coordinates of the location of the object. Maybe also the window size, right, of the size of the face. It could also be the landmarks of the face, right? So you want landmarks of the jawline, the mouth, the nose, the eyes, as I've shown you before. But maybe you want yi to be classification, in which case yi would be 0 or 1 or negative 1 or 1 for that object is present or not present in that image or in that window or whatever input you give it, right? So it could be either classification or regression. All right, so the very first option that you have when you have a problem like this is to use the square laws, right? What's the square laws? The square laws, maybe I'll add the 2 here to specify this is a square laws. It's f of I given my weights w, right, comma yi. So this is the output of my network compared to the expected value. That would be, if I'm using the square laws, 1 over q, the sum of j from 1 through q of fi ii w, or I'm sorry, that should be j, excuse me. Actually, f j ii wj minus yij squared, right? This is a square law, you agree? So this is now the image. I have f, right? My function f, it's a function of functions, right? Correct? It's a vector of functions. And the reason it's a vector of functions is because if I only have one output, this is a face or not a face, 0, 1, then I only have f1. If I have the coordinates of the location of the center of the face and the width of, or the size, the scale of the face, then I have 3 parameters, so q is equal to 3, right? And so on. So this is what I have. And the optimizer, right? When I optimize, I get this j function, and I get, say, these new weights, these optimal weights, w tilde or w star, if you prefer, which is more typical, which is the minimum of that square laws here, right? That I have defined, right? Okay. Now, as you know, the square laws, or the least squares laws, if you prefer, is susceptible to outliers. Very good, right? You remember that. Excellent. So what's going to happen? Ideally, what you want, for example, let's take an example. Let's say that I want to detect the landmark points on the face, right? The jawline or the mouth line, right? What I want is I want Fij, which is, I'm going to simplify this. You see this function here? I'm going to call it Fij for simplification. Means the jth function in the ith image, okay? Minus the expected output, Yij, right? If I compute the 2 norm of this, right, this should be more or less the same error, should have the same error once the network is trained as, say, Fik minus Yik, right? Correct? You don't want to be detecting this point right here very accurately and this one, like, half a phase away from the actual point. You want the error to be distributed equally, to be small, right? But to be distributed equally across all the fiducial points that you want to detect. But we know that least squares, right? This least square solution here is not going to give us this, because whatever the larger error is, this is going to actually increment exponentially by the square, right? Or polynomially by the square. And it's going to make it larger, and it's going to try to reduce all the other values as much as possible. But we're going to end up with one of these values, right, being much, much larger than the other one. And that's not desirable. So to avoid this, we need to define a different loss, right? And that's the problem that you're going to face in your whatever application that you're considering applying machine learning to. So let's see how we solve this problem, for example. To avoid this, we wanted to consider, instead of each point independently, so you see here, I'm considering, say, the location of the corner, the right corner of the mouth, right, that the network estimates compared to the actual location, right? And then the estimation of the left corner compared to the actual left corner position, right? Every point is considered independently. Why? Why don't I consider pairs of points, right? So imagine that I consider pairs of points instead of just single points. Now I can write the following loss function: 2 over q plus 1. The sum, and I'm summing here, let's see. I'm saying jk, it's a pair. J has to be equal or larger than 1, and k is smaller than q, or equal than q, right? And obviously j is smaller than k. And now I'm computing the distance of Fij minus Yij minus Fik minus Yik, right? Maybe to the power of some value a, with a larger than larger than 0. Let's do that. Typically larger than 1. Let's say larger or equal than 1 makes more sense. I don't want it to be quasi-norm. I prefer it to be a norm. Oh, that's exponential. That's not. Oh, okay. All right. True. That would be useful, right? But that doesn't really truly solve the problem. The problem, so this is a possible solution, right? This new loss. But the problem that I really have, it's not this, right? Or it's not solved by this. The problem that I really have is that I have it up over here. I want this to be proportional to this for some norm that I want to decide to use. Let's say I'm using norm P, okay? I want them to be proportional or very similar. So in fact, what I can do, even better than this, or to assure this, I can say that Fij minus Fik, given a norm B, right? Now Fij minus Fik is going to give me the distance, for example, from the right corner to the left corner of the mouth, right? As estimated by the network. And what do I want? I want this to be approximately the same as Yij minus Yik, which is the actual distance, right? You see that? And by just making this tiny change, now I can redefine my loss function as 2q plus 1. Same as before. Now I have g of h of Fij minus h of fik minus g of yik minus ij, excuse me, and ik. And maybe I'll square this. Or you can add an a as we did before, if you prefer a larger or equal than 1 here. Okay. Well, actually, larger or equal than 2. Let's leave it as a 2 for convenience. Now here, h, in this case, is a function that restricts the space of possible or allowable functions in my space H of possible solutions, right? My hypothesis space H. So H, small h, is the constraints on capital H, right? So for example, if I'm looking at fiducial points, then in general, h of fij, it's just going to be fij, right? There's no restriction. It's just the location of the landmark points. There's no. But let's say that I'm doing classification instead. Instead of regression, I'm doing classification. I give you an image or a window of an image, and I want you to tell me, in that window, do I have a face or do I not have a face, right? 0 or 1. Then, or -1, +1. Then in that case, h of fij would be equal to the sign of fij. Okay? So the output would be either -1 or 1. Okay? So why is that useful? Because the network, remember, the network is actually a regressor, right? Like in logistic regression. The network at the output will learn to output a negative number or a positive number. Negative number, I'm on the negative side of the hyperplane. A positive number on the positive side of the hyperplane, or the nonlinear manifold that separates the regions of the space, right? So that's H. And then G is nothing else than your metric, right? The metric that you want to use. Okay. So for example, G could be, as an example, G could be, as we defined above, the B norm, right, of your vector. All right. Now, why is this so cool? Because this definition that I have here is better than the one I had before, because it uses pairs of points instead of just single point. But the least squares problem still remains, right? If I use b equal to 2 and I have the least squares problem, the least square solution, it is still going to be biased toward the differences that are larger, right? But now I can trivially extend this to triplets. Let's see that. So to extend this to triplets, now it's trivial. All I need to do is to define, now I'm going to have R3 inverse, right? R over 3. Now the sum of, now I have J smaller than K smaller than S. And now here I have G of H Fij, comma, H Fik, comma, H Fis. And that I'm going to compare it to, this I'm going to compare it to G of Yij, comma, Yik, comma, Yis, right? Square. So you see what I did? All I did, I still have G, my norm, right? But now my norm is given by this triplet. So if I have, remember, if I have now G of, say, 3 vectors, x, z, u, the norm is going to be x minus z plus z minus u, right? B, that's the norm. You see how this works? But why am I going to use this norm? I could use whatever else I want. I need to use a measure of similarity, right? So I could use instead, I could compute the area of the simplex. Simplex is nothing else in this case that I have a triplet is a triangle, right? It's a 2D simplex or triangle. And what would be that equation? It would be 1/2 of x minus z cross product x minus u. Do you see how this works? And that computes the area of the triangle defined by this triplet. Okay? So now I compute similarity based on the area of the triangle rather than that metric. And why is that even more preferred? Why is this preferred? Because now I can use a famous theorem that used for certain learning in calculus called Green's theorem that extends this to any number of points, t. So you can actually use this for all the points that you want. And now you have a general solution. That's your loss function. It's beautiful. And it's a simple equation. I'll give it to you next time because I'm way over time. With that Green theorem, you have this beautiful loss function as a result. All right? OK, I'll see you Thursday.